Hello everyone. So it's the second class of this course. So today we'll discuss the second contest. It was a little bit more difficult than the first ones, I think, but not that difficult. I think all problems were kind of approachable for you. So if you solved not all of them, it's not a problem. So maybe you just didn't have enough time to do it. But I think that all problems actually didn't require any special knowledge. So you maybe need to learn some tricks, but not that difficult. So let's go. So the first problem. Problem A is actually pretty straightforward. So they ask you to calculate something, and just by analyzing this problem statement, you may understand what's going on. And it's actually a simple math problem happening here. So it's again the one of the main themes of this course will be it's very important to read the statement. So the most important part of solving the problem is just to read the statement. So you need to read the statement, understand what's going on, and this is like half of your solution. Sometimes statements are especially written to be complicated, like in this case. No, it's not very difficult. So it's like three paragraphs of text. It's not that difficult, but still you need to understand what's going on. And what's going on is a pretty simple thing. So we have two persons. We have Harry Potter. Okay, Harry Potter and Voldemort, I believe. So they stand in here and here. Important constants is the length between them is L. And they charge some spells to each other. So charging spell here, he charged the spell from here. They meet at some point, then we go back. Then we go back again, and it's easy to see actually if you try to do it. Then they will meet at the same point again. So again, this is just overcomplications of the statement. So the statement says that we need to calculate point when we meet at the second time. So these two spells meet, then they go back, and then they meet again, and you need to calculate this second point. But actually, it's easy to see that the second point is the same as the first, just because of the symmetry. So that's all. So you just need to find this point. You know the speed of the first one, speed of like p, and speed of this is q, and you just need to find this point. And it's just simple math problem. So you calculate length of this segment. So this length of these two segments, they correspond the same as the p and q. So this length of this segment will be L multiplied by, what is the ratio of this part? Is p divided by some p plus q. That's all. That's all. That's the whole problem. So what do you need? You need to read three numbers and output this number. What can go wrong? Not that much actually. So again, let me implement it really quick. What people may do wrong. If you use C++, some people use floats for some reason. Still, don't use float in competitive programming. Just never. So there are situations when you need to use floats, but they are so rare. So you probably never will face a situation when you need to use float instead of double. Just always use double. In soft level, there are two important: double and long double. You can use long double everywhere, but I don't recommend using long double everywhere. They're a little bit slower and use more memory. You probably don't need it. You probably you just use double and should be enough for like 99% of problem. Sure, I read them C L P P P X and Q, and so L multiplied by P divided by P plus Q. And if you just implement it like this, again, if it is the first time you see problems with floating point numbers, again, okay, this will be fine here. Run again. Okay. So it looks fine, but if you submit it like this, let's try to submit actually. It will probably get a wrong answer. I believe so, at least. Will it? No, it's okay. Even like this, because all numbers here are pretty small. It is because the improvement. Okay. So in this problem, so it's especially the first problem. So it's designed to be very easy. So they ask you just 4 digits here, and numbers are pretty small. Problem is if you in some another problem you ask to do something like this, you probably need to have more digits. So let me to my submissions. Okay. So if you look here for like here for example. So the correct answer is this, but I output this. So I output enough digits to pass the test, but actually I just output 6 digits here. You see, 6 digits. I actually can do more. So normal double type has like 15, roughly 15 digits. So I can actually output more precise answer. And in some another problem, you do it like this. You get set precision here. I usually set to 20 just to be sure. Okay. So this code does actually the same as the before, but when you output the result, you output more digits. Okay. So in this problem again, there's no difference. Okay, it will test at some point. So in this problem is no difference, but in some another problem, if you see something like this, be careful about this. So again, this is how I output doubles, like always. Sure, like this, like just set precision 20 is always enough. So don't think about it. No, come on, let's do it. My God. No, you see, I output a lot of digits now. You probably don't need that many digits, but it's good enough. Basically I output as many digits as I have in my double. So double just output all the digits that it has. Okay. So that's problem 1. Pretty straightforward. No implementation problems. Just apply one formula and solve this again. Let's go next. A problem requires equation. Okay, a nice problem again. You need to read the statement, understand what's going on. So what's going on in this problem? You have some bottles. You need to make all the bottles the same. And to do this, you have BB liters of. That's basically it. So what's happening here? I have some. You have some bottles. Okay. 1, A2, A3, and A4. And you just need to equalize them. You want all bottles have the same amount of liquid. No, again, how you solve problems like this? No, you just think manually. If you have situation like this, what should I do? I want to have all amounts be same. So first, how can I do it? No. First of all, let's see. So I have some maximal amount here. So if I want to equalize it, I probably need to have at least that amount in all other bottles. So if I add enough water to each bottle, not it codes. Friends group. How this? It's not bottles. Yes, it's one bottle, but this is mugs. Okay. So if you add enough water to each mug, so they all match the maximal mug. Yeah. So now I have an equal amount of water in each mug. Then what you do? What's the problem? I need to insert exactly B units of water. So I have this number B. So if people just ask me how much liquid do you need to equalize all the mugs, you just calculate. You just find the maximal mug and calculate this difference, sum all these volumes, and get the total volume water you need. Problem is you don't need to calculate how many water you need. You need to split exactly B units of water. No, And again, it's easy to check. So what we do next? So if we know this number b, we'll see. So we need this amount of water to equalize everything. If b is more than this number, then we will split the rest just in equal parts. So we'll have some equal parts here and add them at here. So again, we do it in 2 steps. First, we equalize everything, see how much water we used. And if we have any water rest, we just split it equally and just add this water to the rest. That's all. Let's implement it really quick. Do it. Let's see your implementation just from. Who was the first one? Oh, it's hard to find. It's just 7 minutes. Okay, let's see. Oh, again, I forgot. First do here, then do here. Yeah, you have a nice implementation. So again, we input all the numbers, find the maximum. You can do it in single line. If you for some reason forgot how to do it, you can always do it using for loop. So finding maximal element is not a big problem. So if you forgot this function, like I usually do, I don't remember functions like this. So I just write a simple for loop and find the maximal element. It's just I don't have enough memory to remember all this stuff. Okay. Here we will no. Okay, also it's also possible. You calculate total volume and then subtract the volume you already have. And then now you understand how much volume of water do you need. If you need more than you have, then -1, and if else, you subtract this amount you need, and then add the rest. This b. Now I subtract b. Now this b is the amount of water rest. I just divide it by. Oh, I use long doubles. Okay, why not? Okay, long double just to have more digits than double. In this problem, double is enough, more than enough. But you can use long doubles if you want. Yes. Third problem. So in third problem we have So third problem looks scary. Okay. So starting from the beginning, you have some permutations. Some definitions here. You have very mathematical look like. And here you need to build something. So it's just not you need to calculate something. You need to build some object. When you need to build some object, it's always scary because you don't know how to build it. Yeah. What object we need to build? We need to build the object with some strange formula equals to 2k. Looks always this big formula looks very scary. Yeah. So. How to approach scary problems like this? No, first of all, you don't be afraid of these problems. So even if it looks scary, you just they look scary because the problem authors want it to be scary. Yeah? So they just want some scary formula in the statement. Probably this if you look deep into this formula, it's nothing that's crazy going on here. So let's look at this formula. So what we have. So we have difference of two parts, like left part and the right part, and they almost the same. Yeah. Let's look, for example, at the left part. Yeah. So what we have in the left part. So we have difference, like absolute value of difference. Yeah. Between two neighboring elements. So we have element 2i minus 1 and 2i. Yeah. So what's happening? We split all elements into pairs. So you look elements. Let's say like A1, A2, A3, A4, A5, A6. Good enough. So what we have here for I equals 1, I have difference between 1 and 2, so I have difference between these two elements. Yes? And have sum of all this. So I have difference between these two elements plus difference between these two elements plus difference between these two elements. Okay, so this scary formula is actually calculating very simple thing. So I calculate difference between first two elements, difference between second two elements, difference between these two elements, and then sum all these differences. Not scary. Yeah? What's happening in the right part? Almost the same thing. But I take this absolute value out of this sum. So I first calculate sum of all these differences, and then calculate absolute value of this sum. Okay, can you please mute? Yes, yeah. If you don't plan to talk, thank you. Then, now, what you can think? So again, so this is the first part. Now let's think. Let's look at this formula in another way. So it is sum of some values. So in first formula I have sum of, let's say, no, let's call this difference like I have B1 and B2 and B3. Yeah. So in the left formula I have like model B1 plus abs of B2 plus abs of B3. And in the second formula, I have abs of this sum, yeah? B1 plus B2 plus B3. Well, now you need some mathematical again intuition of thinking about what does the formula means. So first of all, I think why these parts are different. They look kind of the same. Here I have sum of 3 elements. Here I have sum of 3 elements. So for example, if all elements are positive, so I have 1 plus 2 plus 3. And here I have 1 plus 2 plus 3. Yeah. So if all elements are positive, then this sum is actually the same as this sum. Yeah. So sum is 0. Yeah. And if all elements are negative in the same way, so if we have minus 1, minus 2, minus 3, then here again I have 6, yeah, and here I have minus 1, minus 2, minus 3, so sum is minus 6, I said. Minus 6, and then I calculate absolute value, and again I have 6. So if all numbers are positive, I have 0. If all numbers are negative, I have 0. Again, what I'm doing here, I'm trying to play with this formula if I don't understand yet what's happening here. I'm trying to play with this formula until I understand what's going on. Yeah. So here I see that all elements are positive, I have 0. All elements are negative, I have 0. So the only way to this formula to be non-zero is by having some positive elements and some negative elements. Then what will happen if I have some positive elements and some negative elements? So let's see. So let's split them. So you have some positive elements and some negative elements. Yeah. And here we have sum of all this. Again, you have the same elements positive and some element negative. Yeah. Here, well, let's say that sum of all positive elements is, let's say, x, and sum of all elements is minus y. Yeah. So just say it is negative. Yes. So x and y are positive. Yeah. No, non-negative, doesn't matter. It may be zeros. That doesn't matter. So 0 doesn't change anything. So I have x and minus 1 here. So what will happen? So and here I have x and minus 1. Then in the left part, I calculate absolute value of every element. So the total sum will be equal to x plus y. Yeah? Here I have x plus y. Yeah? And in the right part, I calculate modulo in the end. So it's absolute value calculated only in the end. So I first calculate this x minus y, and then calculate absolute value of this. Now, let's say for simplicity that x is greater than y, greater or equal, okay. Then this value is non-negative, so I can remove this model. So I have x plus y in the left, x minus y in the end. Okay, again, what I'm doing, I'm just trying to play with these formulas, and I introduce some strange variables here. So if you don't know how to do it, you probably need to solve more math problems, because it's like standard things you do with math problems. So I see that I care about positive numbers and negative numbers. So I introduce like positive sum, negative sum, and then try to rewrite my formula using these elements and hope it will be more simple. Okay. You have minus this. So what we and now I have very simply, so x plus y minus x minus y will be x minus x is 0, y plus y is just 2y. That's all. Now let's move back to the problem. Now again, this is I'm still far from solving the problem. Yes, right now I just play with formula to understand how this formula works. Yeah, Now we need to go back. So now we understand how this formula works. So in this formula, we care about positive and negative values. And we have some elements positive, some elements negative. So if for example positive elements, sum of positive elements is x, sum of elements is negative elements is y. I look at the smaller. So in this case, I have I'll say so this is 2y if x is greater than y. So I take these two numbers and smallest of them, if it is y, then the total sum will be 2y. Yeah? And I need it to be 2k here. You see? Okay, so now what we need to do? Let's go back to our problem. We need to construct a permutation in such a way that some elements are positive, some elements are negative. Yeah, and the sum of all elements. So some I have. If I have sum of the positive and sum of negatives, smallest of this sum should be equal to k. Yeah, so I need this y be equal to k. Yeah, to be this total sum equal to 2k. That's basically it. Now you think, okay, how I will construct permutation with positive and negative elements? There are many ways. For example, what you can do, easiest way if you don't care about numbers. So what you can do? So you can take permutation 1, 2, 3, 5, 4, 5, 6, 7, 8. Yeah. Now every difference here equals to, we take left minus 1, so minus. Now every difference is minus 1. What I can do? I can swap two elements in a pair. Like here, I make 2, 1. Then the difference will be 1. Let's swap in every pair. So I have 6, 5, 1 and 8, 7, 1. So here I have x equals 0 and y equals number of pairs. So length of the sequence is 2n. Yes, 2n. Yes, of that 2n, yes. So I have n elements, so y equals to n. And here I have x equals to n and y equals to 0. Ah, 2k not greater. Okay. I thought k not greater than n. 2k not greater than n. That makes sense. Now, and I want the situation when x is greater or equal than y, and y equals 2k or 2k. Yes, and k is not greater than n over 2. That's important, yes, because 2k is not greater than n. Okay. No, let's just move from this situation to this situation. So we move to this until we have y equals to k. When y equals to k, then x will be equal to n minus k. Yeah. And then we just see that the constraints are actually good in this problem. So okay, that's lucky me that problem also actually give a good constraint. So if k is not greater than n over 2, then n minus k is actually less than or equal than y. And that's also. So what is the final solution? So I swap. I divide all elements in pairs. So I want first, let's say, k pairs to be a negative. Okay. Small number and then big number. This k, this n minus k. I want to have k negative pairs, so every pair will produce minus 1. And I have n minus k positive pairs. Yeah. So you produce negative pair by saying like 1, 2, 3, 4, 6, 5, 6. And you produce positive pair by swapping these two numbers. So like 8, 7, 10, 9, and so on. That's all. That's the whole solution. Again, what's the difficulty of this problem? Difficulty is that the problem consists of many steps. So you need to research a lot basically. So it's a small research. So you have some strange problem and you just investigate what's going on. So you play this formula to understand how it works. You play this object like permutation and how this permutation applies to this formula and so on. And then after some time playing with this formula, you actually understand what's going on. And then you think how you construct the permutation that produces the given result. Not easy problem. I agree. So if you think this problem was too hard for you, probably yes. But again, many people solve this problem. Good for you. Good for you. Let's check some solution. Someone else, probably not. Let's check you. Okay, 21 minutes spent for. Here we just check that you correct. Okay. Oh yes, okay. Yk equals 0 is special case for you. I'm not sure yk equals 0 is special case. It should be special. I believe it will just because you apply the first oh no, it's you do it like this. You okay? It's a different solution. You play 1 and k plus 1. Nice. Okay. Okay, you create another construction. Okay. Okay. So you start by making this sum equal to k, and then you try to make everything 0. Yes. Also nice. Nice solution actually. It's different, but again, if you do it that fast, good for you. Good for you. Like this one. Okay, that's the same as I expected. So okay, so again, you just make this. Okay, so here you make the okay. What this code does just create array of 1, 2, 3, and so on. So we create this one, and then there's swap elements of the first k pairs. Yeah. Good. Problem D and problem. What we have in problem D again? We have some very strange written statement. Exactly one digit to the number to the right produced an example is divisible by b. I forgot the problem. I solved it before, but I just forgot what's going on here. Sorry. If it was a top 10 divisible by b by the first which pronouns can play the operation n times. Can I just add zeros? No. Why can I add zeros? I can add zeros. Can? Yes. So again, there are multiple ways to solve this problem. This problem, what is the important part of this problem? We didn't talk about it before. I mean, it's just the second class, so we didn't talk about much stuff. So what's interesting in this problem? We're talking about divisibility. Yeah, so we want some number to be divisible by some another number. How do you usually maintain divisibility? You only maintain current remainder. So you have your number a. You only maintain remainder this number modulo b. So you only care about this number. You don't care about number a anymore. Yeah? Because you only care about divisibility. When you only care about divisibility, you only care about remainders. So instead of having number A, let's care about numbers. Let's call it number A prime. Yeah. So it will be just remainder modulo B. Now, what's interesting about remainders that you can apply normal operations like if you have numbers A plus B, you want to calculate this sum modulo like let's use another numbers. I already use A and B here. Let's use it here. So if you calculate, let's use here. So if you have x plus y modulo sum m, so you can first take x modulo m, then y modulo m. So you can apply this modulo A everywhere. Just apply here and then calculate this sum, then calculate modulo m. So you only work with small numbers up to m. Yeah. So we do the same here. We only care about the current remainder modulo B. Now, what's happening when we add some digit to the end? So we have some number A, and we add some digit here. Let's say digit x. So let's remove this so I don't have conflict of variables here. Okay. So if I add digit x here, so my next number will be 10 multiplied by A plus x. And since I only care about remainders, I can calculate like this. I will calculate my those will be 10 multiplied by my all remainder here plus x and this all modulo B. And now I just need to find this digit so my number is divisible by b. So I want this to be 0. And you can just iterate through all possible x's. So we have decimal digits rather than just 10 decimal digits. So this x should be something from 0 to 9. You can just check all digits from 0 to 9 and see if it produces if they produce number divisible by b or not. It's one way to do it. Another way is actually just look at this number and so if you look at this number, so I want this to be 0. Yeah, let's make it like this. So I want 10 from plus x equal to 0. Everything modulo b. Yeah? So you just can, like you do in normal arithmetics, you can drop this part to the right and say that x equal to minus 10a. Now let's just remove prime just for simplicity. Yeah. So x should be equal to minus 10a modulo b. So actually you can find this number x just using math. You don't need to iterate over all. But you also can iterate over all of them. Also possible. Since everything is small in this problem, you can do it like this. The important part, again, maybe the important part of this problem is so when you add these digits one by one, you get pretty huge numbers. Yeah. And working with these huge numbers is slow. So if you just add digits one by one, every time you calculate the remainder of this long number, it will be slow. So you don't want this. So instead of working with big numbers, you only work with remainders. I believe that's the main idea of this problem. So you may miss in this problem. That's all, I believe. So let's look at one of your solutions. Who else? Let's pick someone else. Let's pick you. Oh, it's in Python. Okay. Don't tell me in Python you can do it without. Okay, you're cheating. Okay. Okay, that's what I planned actually. So you find the first digit by using this loop, then you add this second digit, and then after you add the first digit, the remainder is 0. So I have number divisible by b, so I can just add zeros to the end. Yeah. Okay. Then that's again you use some math reasoning. That's good. So yeah. Okay, so in this problem you need to use at least one trick probably. That was long term part. So what can go wrong? Maybe check. Okay, let's check this part. Let's check this part. Oh my god. Oh my god. Okay. When you have something like this in easy problem, you probably going in the wrong way. So if you need to specify some free specific exceptions like this, you probably doing something strange. It's just one specific example. Okay. So if you just have one specific test that doesn't work, probably you're doing something wrong. The purpose first. Okay. You just overcomplicate stuff. Okay. No, let's analyze it quick. So what we're doing here, we're set with why j multiplied by b. I add all multiples of b to my vector. Not sure why, but okay. Then I look at all these multiples, make string out of them. And check if I am the prefix. If the size is greater than s size plus n. Okay. Then break. No, makes sense. And I have two big numbers. Okay. Not sure why you have this break, but okay. And again, it looks like some unnecessary optimization. So if your code if your code didn't work without this optimization, probably you have just bugs in your code. If it is not, continue. Okay, because I'm smaller. Okay, makes sense. I can shorten my number. And here I check if I have the same prefix, right? So I look at the prefix and check if it is not the same, then g is false. Okay, so if g is true, then my string is prefix of this multiple of b. This actually should work. I'm not sure if my number is exactly v, so you need to add this first digit somehow. It doesn't matter. You will just add zeros. Okay. Why you put v? I put s. You took you. About v's. Okay. Now I get it. So v is v. Oh, okay. So v is the multiple of b. I take from n's. I take some multiple of v. Okay. Calculate to string. Okay. And now I take my number string s, add all the remaining digits to get number v, and then add some zeros. Actually looks fine. Okay, it's overcomplicated solution, but it's still correct. So it should work. Maybe here's the problem. What also works is one is 6. Should it be enough? Maybe this is not enough. Let me check. Okay, this was -1. So sometimes answer is -1, but you don't know the answer is -1. How can it? I got it. You need to add only one digit. So after you've added the first digit, the number should be already divisible by b. Okay, so okay. So when you move from s to v, you add many digits. Yes. but you need this number to be divisible by d when you add the first digit. Okay. Let's okay. I believe you. Okay. So here. Which one? I believe you. You just reported. It's boring. It was a nice solution. Why? You just boom. It was almost correct. Let's remove all the non-important stuff. This is non-important stuff. So I need to check that I add one digit. So if this size not equal to s size plus 1, then continue like this. Even for 7, just to be sure. Submit. Submit. Compilation error. Okay. That's usually what happens when I submit without compiling. Good. So while it's testing, let's read out the problem. It's too slow today. I don't know why. No, okay. Problem E, the computer game. No. Problem E is actually a nice problem. So it's okay. So in contrast to previous problem, it has almost no mathematics to it. So it's just read the statement, understand what's going on, and then just write algorithmic solution. So what's happening in this problem? I have a boss fight. So the boss has some health and some regeneration. And I have some spells I can produce. So every spell have some parameter proof. It says when I can apply this spell. So I can apply the spell, then the amount of health is not bigger than something. It's called in percent. Okay, why not? So every spell can be applied when the boss has no more than corresponding amount of health for some reason. Okay, and when you cast this spell, it starts to deal this amount of damage. So every second it produces the same amount of damage. Yeah? That's all. So that's all you can do. So you just apply these spells one by one and just wait till the boss dies. So if it is dying. Again, it's nothing interesting happens in this process. So you just read the display and understand what's going on. It's not that complicated what's going on. So I just have some. You probably. Sometimes they explain it here in the note. Just explain what's going on in the statement. Here they didn't. But again, it's not that. Okay, so we have, for example, here is. Not that difficult to read all this text. You need to read all this text, understand what's going on, and after that, it's kind of intuitively clear what you need to do. So again, imagine you're playing this game. So you have this boss. You have some amount of spells. So every spell deals some damage. So what you need to do? You can cast each spell only once. So what you can do? It's kind of logical to cast a spell that deals as many damage as possible. So you just choose over all spells that you can cast. Just choose the one that deals the maximum amount of damage. That's all. Then wait till the boss runs out some health. Then maybe you need to cast another spell. And then every second you just cast a new spell. If you can cast any spell, you cast a spell that deals the maximum amount of damage. And then you carefully implement it and just see. So all numbers are small. Here is 10. Yes, it's small. It's damage up to 2000. Okay. So this one is up to 2000. So all the numbers are small, so you can do. You don't need any special data structures. You don't need special anything. You just carefully do it. Just simulate every second what spell. Just simulate every second. Check how much health does the boss have. Which spells can you cast? Select the spell will deal maximum damage. Apply this damage. Continue. Just just normal implementation problem actually. You read statement, understand what's going on, implement it. Nothing actually, nothing that interesting. So if you have any questions, I'm actually not sure why you didn't solve this problem. Many of you didn't solve this problem, so let's check some certificates. Which one is the fastest one? This one. Okay, that's basically it. Yeah. So again, you calculate, you count the seconds you deal the damage, calculate regeneration. If you have then the monster is dead and you break, then you calculate the current amount of what HP. You calculate the percent. Okay, it's also so you calculate the current percent of health, and just test if it's used, continue. If it's not used, check if it is better than you have. Then in the end you find the best possible spell. Check if it is non-empty. If you can do at least one spell, if you can't do any spell, no, okay, you can do it like this. You can just wait. It's just some time out until it works. That's also possible. So if you can't cast any spell and regeneration is more than damage, it means I can't do anything. The monster just regenerates faster than I damage him. Yeah? So answer is no. If in here, yeah, if I can do any scrolls, just continue to the next iteration. If not, I use this spell, increase damage, and so on. Again, just implementation problem. And it's even not that implementation hardened as we have in the first contest. No, yes, you need to understand what's going on. You need to understand that greedy algorithm actually works. But in this problem, it's quite obvious. If you have multiple scrolls you can cast, you always deal the best one. You always cast the best one. Because you will always be able to cast the previous ones. Because if you're able to cast some scrolls, then let's say the amount of health is not increasing. So if I'm starting dealing damage more than regeneration, then health is always decreasing. Yeah, and after health starts decreasing, if you can cast a spell, you will always be able to cast it in the future. So it's always best. So if the amount of choices is only increasing, the greedy algorithm always works. So you take the best possible choice, because if you have less worst choice, then you can always take it later. Yeah. Again, you don't we need to have special lecture about greedy algorithms, I believe. So sometimes it's not trivial why greedy algorithm works, but in this case it's quite obvious. If you feel like it's okay, you need some experience until you start thing. So you need to, if you don't feel it, just start to argument. So why greedy algorithm works? So why do you think I need to take the best possible scroll? And then again, the reasoning is because if I take the not best possible scroll, I can always swap them. I can always take this first and then take that. Because if I can take it now, I can take it in the future. Okay, it's called safe step in greedy algorithms. Okay, we need to have a special lecture about this probably. 3 problems left. Let's go. Oh, problem F. Okay, I love problem F. How many of you solve problem F? Oh, that's actually a lot. Good. Do you have from Ganser test? Oh, you have from Ganser test 29. Okay, that's fun. From Ganser test 29 is okay. It's nice trap in this problem actually. Not nice trap, just trap. Okay. So what happened in this problem? I need to calculate this sum for all numbers. I have this strange looking distance. It will look almost different actually. It's almost different, so it's difference for all numbers except if numbers are close. If numbers are close, then difference is 0. And you just need to calculate sum of all this for all points. Okay, so first thing, what you think? So if you never see this problem before, let's talk about this now. So if I just calculate the normal difference, so if I just need to calculate, let's say, like sum for all I less than j. Let's say a. No, let's say in this part. Let's say nj minus ai. So if you need to calculate sum like this, so for all pairs I less than j, so you have array. Yeah. You pick all possible pairs of elements, calculate difference between them, and sum all this difference. How to calculate this sum faster than just in n square time? No, in n square time is zero, so you take for I, for j, yes, sum plus equal aj minus ai. So it's n square time. It's too obvious. So how you do it faster than square time? You can do it in linear time actually, just by looking at this formula. So there are multiple ways to do it actually. One way to do it is look at the contribution of each element to this formula. So again, let's look at this array. Let's take some element here. Let's see how this element is used in this formula. So sometimes this element is used as j here, like as left part. So in this formula, I will add this element. I will add it for all i's in this region. So if I is in this region, I will add this element to my final result. And it's easy to see how many times it's happening. It's happening for this element, for a number of elements before me. And sometimes this element is used as the last element, so as this ai. So if this element is I, then j must be one of these elements. That's all. So how to calculate this sum? So again, you take element ai and multiply it by total. Basically, you calculate total contribution of this element to the final sum. For example, I will be calculated as plus for all elements before, like I. Minus, it will be calculated like this here. So again, so for 0, this is I minus 1, this is I plus 1, this is n minus 1. So amount of elements here will be n minus I minus 1. You can rewrite this as 2I minus n minus 1 plus 1. Yeah. So this is contribution of my element to the final sum. So okay, if you never saw anything like this before, that's how it's done. So I believe you can actually invent this solution if you never seen it before. But that's like normal thing how you calculate some strange sums. You calculate some strange sum by simplifying it. You split the sum into elements that easy to calculate. Like here. So I split everything connected to element to a separate group, calculate sum of this group, and then split again, calculate sum of each group, then calculate total sum of all groups. Just by regrouping elements of your sum, you can make fast algorithm. Another way of doing the same basically is like this. You can go from left to right, let's say. Or right or left, which one you prefer. So let's depict this element. So if this element is j, then I is any element from here. Yeah. So what I need to add? I need to add element a j minus a0. I need to add a j minus a1 plus a j minus a2 plus and so on. Yeah. So it is the same. So I calculate number of times I see this. So it will be aj multiplied by, again, number of these elements by j. Yeah? Minus this sum of this a0 plus a1 plus a2 and so on. And you can calculate this as prefix sums, like you normally calculate prefix sums. And this is just multiplication, yeah? So you just go from left to right, calculate this prefix sum, and just subtract this from this and add this to result. So you just basically you again what you're doing. So you split all this big sum into some groups and just calculate each group first. That's all. Okay, so again, this is again what I'm doing first. I look that this formula looks like normal difference. So first, let's again, let's solve the problem when you have just simple difference. If this problem looks like this problem is harder than problem with simple differences, right? So let's first try a problem with just differences. Now let's solve the actual problem. So what's the difference between my problem and this problem? Then sometimes some elements are equal to zeros. So what I will do, I will try to first calculate this sum with normal differences, and then just make small adjustment. So I will calculate number of pairs I calculated wrong and adjust my solution. Yeah? So what I'm doing. Let's just implement this actually. Why I don't know. Let's do it really quick. Int and vector long. I use, by the way, if I used this because I moved from Java a long time ago, and I still use long as 64-bit. So my longs are 64-bit because of this. Some people use long or LL or something like this. I just used to do it like this. Do not copy this if you didn't move from Java. So it's not very good code style actually. Now I will calculate the sum. So sum will be equal 0 for so I multiply by I minus prefix sum, and this prefix sum will be sum of all previous elements. Yeah. Initially it will be 0, and then I will add AI. That's all. So let's just try it. It will produce different result from this because I calculate not the same thing. Yeah. Here I calculate 6, but it should be 4. No, because some elements of this sum are actually different. But here actually I don't have any values. So here I don't have any elements with difference 1. So it should calculate the same result. Oh, it's going to do the same result. Okay. Now we'll make this adjustment. So again, what is the adjustment? I don't know what can you see it actually? Look like, oh, that's better. Let's make some adjustments. So in this part, I counted some numbers as ones or minus ones, but they actually not minus ones or ones. Yeah. So if I have some element aj, let's say, okay, I have ij swapped here. Yeah? So I have aj equals to I minus 1. Yeah? Then in this formula, I calculate this difference as 1. Yeah? Then I have ai minus aj equals to 1. Yeah? But it should be 0. So I need to move this to 0. So what I will do, I will count how many times it happens. So I will easiest way is to create a set, for example, a set of long. Let's see, just use longs here. Let's call it somehow counter. I need map. Okay, I need map. So I will count how many times I found each element, and here I simply need to calculate how many times I saw element ai minus 1. And subtract this. So again, I just make a small adjustment of this sum. I change the element of the sum that calculated wrong. So some elements calculated wrong, I just make this small adjustment. So I fix these elements, and also you need to fix elements plus 1. So if it is ai plus 1, then this difference is minus 1, but it should be 0. So I need to add these numbers back. And yes, you need to update the counters. That's basically it. Let's check it else works. Boom, boom, boom. Oh, should work fine. Okay, and then that's the whole solution. Okay, if you use not C++ but in a Python, it's even so. In Python you have maps like this. So it doesn't call map, called dictionary, but doesn't make sense. In basically all languages you have some types of maps. I believe in all languages. They have underneath they have either binary search trees or hash tables. It doesn't matter here. I don't care about order of these elements. I just need like associative array, so I can use hash maps or binary search trees. Doesn't matter. Sorry. That's all. Now, when you now to interesting part. Why I like this problem in some sort of way. I'm strange preference to problems. If you try to submit this problem, I believe I did it here. Okay, so maybe the solutions. Yeah, can I produce the same solution twice actually? Yes, looks exactly the same. Nice. Okay, so okay, I'm consistent. Okay, so yes, I solved this problem a few days ago, and okay, I produced exactly the same solution. Okay, while testing, so what's the problem? So if you try to submit a solution, you get wrong answer test 29. And then you think, okay, what's going on? How can I be wrong in 29 test? You check everything, everything looks fine. And when everything looks fine, you think, okay, maybe I have some strange problem. Maybe it's not that obvious. And yes, in this problem you have strange problem. Namely, you have overflow problem. It's not usual. So usually when in programming competitions, when you use 64 bits numbers like here, you are fine. So basically, why it happens? Because problem authors they are kind people, and when they create problems, they create problems such a way that everything fits in 64 bits. But specifically for these problems, I'm not sure who are the authors of this problem, but they wanted to trick you a little bit, and these some do not fit in 64 bits slightly. So this resulting sum, you can see that. You can check some. You calculate sum of every pair of elements. You have like 10 power 5 elements, so you can like 10 power 10 possible pairs. Yeah. So 10 power 10 multiplied by 10 power 9 is 10 power 19. Yeah. But 64 bits care about 10 power like 18. So it's slightly less than is possible to fit in 64-bit number. Why people do it? I'm not sure. Maybe because they just fun people want to trick you. There are multiple ways to deal with this. So again, I believe the trickiest part here is to actually understand why you have wrong answer. So after you have wrong answer, if you understand why you have wrong answer, you just need to find the way to deal with it. But again, to understand, to fix the problem, you first need to understand the problem, and that's tricky. Yeah. So let's see how you deal with this problem. For example, okay, you have wrong answer 29. Oh yes, that's how I do the problem. Okay, I have almost the same solution. Yeah, what you can do, you can use, so if 64 bits are not enough, then you can use 128 bits. So modern C++ compilers have 128 bits. When I was young, we had 32-bit integer as a long integer. It was okay. I'm too old for this stuff. Okay, so when I was young, we have like 16-bit small integer and like 32 bits well big integer, and then they introduced 32-bit systems, and like now 32-bit is small, 64 is big, and now we have 64-bit processors, and we have 128-bit integer data type. That's good. So you can actually use it. So in contests. Absolutely normal. Normally, you use this type when you need to multiply two big numbers. So in some problems, for example, all the numbers you're working with are relatively small, but sometimes you need to multiply them and check something. For example, you need to check two fractions, which one is greater, which one is smaller. So you need to calculate this multiplication. Let me tell you what I'm talking about. Just so you know. So, for example, you have all numbers. So, for example, all numbers are small, but not relatively small. But you need to check if a divided by b is less, let's say, than c divided by d, and all the numbers are like 10 power 18. So they fit in 64 bits. But to perform this check, you actually, how do you check this? You check this AD is less than BC, yeah. Like normally, you multiply this, yeah. And here, when you multiply these numbers, you are out of these 64 bits. So when you perform this check, you can go to 1 to 28-bit numbers to perform this check. But you maintain all the numbers in 64 bits, like this. In this problem, you can actually keep all numbers in 164 bits. Why not? So you just keep everything in 128 bit. The only problem is with this number is there is no function to print them. Yeah. So to print them, you need to write special. Yes, that's the same as I did. Yes, you just create a special function that produces string of this number. And here I have. But can it be? It can be negative. If it is negative, you produce like this. Yeah, I just added this to string function. Okay. Yes. So again, you are programmers. Okay, you know how to program. If you have number, you know how to transform number to string. Just implement this. It's not that hard code. Divided by 10. Okay, get remainder modulo 10, divide by 10. Get remainder modulo 10, divide by 10. You take all digits in reversed order, then you reverse them in the end. Ta-da! That's all. It's okay. It's not hard. Okay, just you need to spend extra time on this, but it's not that hard. So if you face problem like this, just deal with this. Okay. Another solution of this problem is actually to use Python. In Python, you don't have restriction on size of the integers. All integers are long integers. So you just rewrite the same thing in Python, and anyone try to do it? Why it's so slow today? I'm not sure. Oh, okay. Oh no, also to string. Okay. Okay, we'll do that. So again, another solution is just do all the same. Let's check my solution. Just rewrite everything in Python. And it's even shorter than the C++ solution. It does absolutely the same. Again, you have dict is actually mapped from C++. Okay? That's all. So you do all the same stuff in Python, and you don't care about overflows anymore. Problem G. Problem G is actually a good one. So what we have in problem G? We have some strange. So again, we have some strange game. If you don't know how to play Hanabi, it doesn't matter. So we have some strange game, and the rules are explained basically here. So you have some set of cards. You need to check which card is which, and to do this, you're given some clues. Hints. Okay, so we're given some hints, and hints are of two types. I can mark all the cards of the specific color, and I can mark all the cards of the specific value. And you need to give minimal number of hints such that you can understand which card is which. So you know the set of cards. You need to understand the order of these cards in your hand. Again, looks really complicated. Very well. What is the first thing you should notice if you have problem like this? You should notice that all numbers are really small. I have just 25 types of cards. Yeah. So I have 5 colors, just 5 values. Now I have 100 cards, but I have only 25 types. So if I have 100 cards, then a lot of them are the same actually. So what it should give you what idea should give you? So if you have problem when all numbers look very small, you think about some non-polynomial solutions, some backtracking, some dp over subsets, or just iteration over all possible subsets, and so on. So think about some solution that involves some non-polynomial steps. Yeah. So basically, you want to iterate all possible For example, you have 25 types of cards. Yeah. You can check all possible subsets of these 24. It will be 2 power 25. It's not that much. It's not clear what to do next, but still, again, this is the first hint of this problem statement. If all numbers are small, you think about some non-polynomial solution. It not always works, actually. Sometimes judges specifically give you some small constraint, but the problem can be solved in polynomial time. Also possible. But in this problem, again, now, what's difficult part in this problem is actually to understand what we're looking for. So we're looking for some set of hints. Okay, let's give some. Let's take this example. So I have G4, I have R4, R3, and B3. Yeah? And you can give 2 clues. Your first clue may be, which one? Let's say red. So I will mark all the red cards, this card and this card. And then I mark all the frees, for example. I will mark this card and this card. So I know this card, so it is red and it is free, so it must be R3. Now I know this card is also free, but not this. So I know this card, and by conclusion I know this card. Okay? So this is how you do it using 2 hints. But it's not that trivial. So how do you say if this set of hints is enough or not? Let's think about this part. So first, you think about what you're looking for. So you're looking for a set of hints. These hints should define all the cards. So you can look at these hints and know the type of each card. How to say if it is enough or it is not enough? It's a good question, actually. So it's not that trivial. Again, like I did here. So you may do some strange moves, like you say, okay, some cards I know exactly because I marked both color and value, so I know this card. Now some cards from this I can deduce by exclusion, so this card is also free, so I also kind of know this card. And then card by exclusion this, and then by exclusion this. It's possible to think about way, but you never know if, again, so you try to deduce the types of all cards by just doing some strange actions, just by small steps, and you never know if these steps are enough. Another way of thinking is what you can do. So how you can produce. I will explain you how can you produce the correct solution in this case. You may think about like this. How can I say that my hints are not enough? So imagine you have some set of cards. Someone give you some hints. And you think like you don't have enough information. What does it mean you have not enough information? It means there are 2 different permutations. Yeah. So for example, I have 2 cards like A, B, and C. And someone gives me some hints, and I don't know, is it ABC or is it CAB? Yeah. So I don't know which one of these permutations is actually correct. Then I think, how can it happen? How can it happen? No, because let's look at any incorrect position here. So in this position, I don't know which card in this position. It may be card A or card C. So if I don't have enough information to restore the permutation, it means that for some position, I don't know which card is correct. How can it happen? No, it can happen only I cannot distinguish these 2 cards. So these cards A and C are actually indistinguishable. So so what does it mean? It means I receive the same information about these cards. So for example, in this case, okay. if I have some, so if I have some, if I mark, let's say I mark green cards and fours. So green cards marks only this, four mark this and this. Yeah. Then these two cards are indistinguishable. Yes. These cards are both not green and they are both not four. And if I have any pair of cards that give me the same answer to all my hints, so in this case I have so I mark green cards. So this card is green plus, this is red minus, minus, minus. This card is plus, plus, minus, minus. Yeah. So for these two cards I have the same answers to these hints. Yeah? They are both not green and they are both not fours. So if I have pair of cards that give me the same answer to all hints, I cannot distinguish these two cards. It means I have no. This set of hint is not enough. Now I think if this situation didn't happen, if for any pair of cards I can distinguish them, is it enough? And you understand this actually is enough. So if all cards give you different answer to hints, so basically this vector of plus and minuses is different for every card, then you can put each card in the corresponding position. You know, so for every card you have this like vector of plus and minuses, and for every position you have vector of plus and minuses. And you can just put each card to its corresponding position. Okay. Okay, hope it was clear. Now, when you understand what's going on, so now you understand what you're looking for. So you're looking for set of hints, such that for every pair of cards, there is at least one hint that is answer is different for these cards. So for example, okay, so let's see. So if I have two cards, copy break, let's say G4 and R3, yeah. So I need to distinguish these two cards, yeah. So if I give some bad hint, like I don't know, blue, it will give me minus and minus. Not interesting, yeah. So I need to give some hint that gives plus for one card but minus for another card. No, what are these hints? No, you can ask for green, it will be plus minus. You can ask for red, it will be minus plus. And if they have different value, you can ask about value. You can ask about 4, it will be plus minus, or 3 minus plus. So you can give one of these 4 hints to distinguish these two cards. Okay, that's all. That's all. So now again we moved from initial problem to this problem. So what we're actually looking for? We're looking for set of hints, and the constraints we have are like this. For every pair of cards, we have some set of hints. So at least one of these hints should be given. And now we have something called set cover problem. Not very interesting. So this problem is actually quite standard. So probably you didn't face before. So if you know how dynamic programming on subsets works, probably you saw it from before. But this is the basic classical subset cover problem. What I want to do? I have some sets like this. I want to cover all the sets using the minimal amount of elements. So I pick some elements. So in each set I have at least one element. And this problem is known in P-hard, but I have small number of everything. So what is the total number of hints? I have 10 possible hints. Yeah. So I need to pick some subset of these 10 hints. There are just 2 power 10 possible subsets. I can iterate over all of them and just check. That's all. So again, the final solution is like this. You iterate over all possible subsets of hints that you give. There are 2 power 10 possible set of hints. Then for every set of hints, you check if it is sufficient or not. You check it by looking at each pair of hints. I think probably you need to pre-calculate something. 2 seconds. Probably you can just do it like this. You just look at every pair. You can do it beforehand. So you can check first for every pair, find this set of possible hints. So you just to make this final check faster. Yeah. Let's look at some of your codes, for example. Which one? Let's list plus. Pum. Oh. Okay. Maybe then you'll have this more simple code. Okay, this looks more simple. Okay, so I count number of cards here, right? Must count at least. Here I iterate all possible sets. Split. Here you just check. Okay. No, okay, why not? Here you use 2 loops to pick the first card and the second card. So you look at all possible pairs of cards and see if you can distinguish them or not. Here you check if you have both these types. Here you check if you can distinguish them or not. No, yes. And if you can distinguish every pair of cards, then flag is true, then you update your result. Here, built-in pop count, just calculate number of 1 bits in your mask. Yeah, my solution is quite similar, I believe. No, I do it like this. So I look at all cards and check if they have different color. So for each pair of cards, I make mask of all good hints. Put all these sets in the set queue. So now check is very easy. So I just need to check for every element in Y. I have this non-zero. So I have at least one element from every set. Good. That's all. It's problem G. Again, this is hard problem. So you need to understand a lot. You need to program. Yes, that's the real problem. Yes. If you solve this problem, good for you. Someone upsolved it. So some problem solved after the contest. Good. Try to solve it. So if you didn't solve it during the contest, try to solve it after the contest. Okay, final one. Okay, this is the, okay, do we have, 30 minutes, okay, let's, don't have enough time to do it, okay, let's try. So what we have in this problem, we have a cycle of elements, basically, and we need to group these elements into blocks, so we have, basically we have cycle of elements, and we need to group these elements into blocks. Let's do maybe one element in the block, maybe more elements, such that sum of elements in each block is no more than b. And we need to split them in minimal number of blocks. And we need to do it for several values of b, because I think this because so they do it for 15 times. I think this because they wanted to solve it in linear time. So you have 10 power 6. So if you solve it in n log n time, you have 10 power 6 multiplied by log is like 20, multiplied by 20. That's a little bit too much probably for 3 seconds. So maybe it fits. Because there are easier solutions in n log n time, but they want to do it in linear time. Okay. What's the trick of this problem? Trick of problem is you have this cycle. So if you have the same problem, but you have them in a row, so if you just break this cycle and if you have row of elements, and you want to split them into groups, such that each group is not greater than b, then how you do it? You do it using simple greedy algorithm. You just go from left to right and take as many elements as you can until you have group of size more than b. So you have maximal amount of elements, so group is less or equal than b. So if you add this element, you have more than b, yes? So you stop here. And then you take next element and so on. So you just apply a simple greedy algorithm, go from left to right, take the element, when you, if your group, if you can add this element to your group and your sum is not greater than b, you just add this element to your group. If your sum is greater than b, then you stop this group and move to the next group and so on. Very simple. The only trick is we have not array of elements, but the cycle of elements. So we have this cycle. What's the difference with cycle? How to deal with cycle? So if you have problem which works not on a okay, cycle is kind of linear structure. So if we like break the cycle here, yeah, we will have the same linear structure. So we have problem on array. The problem is we don't know where to break. So we don't know where we need to break the cycle in such a way that we produce the optimal result. So there is some optimal answer. We don't know how to break. So if we know the optimal answer here, so we can break between some of the segments of this optimal answer, but we don't know optimal answer. Yeah. Okay, now you need to think, okay, that's a tricky problem. So what you do next? It's actually, again, the goal of this class is to give you explanation how you can find this solution. I'm actually not sure how people find these solutions. I can tell you how I did this. So so how I come to the solution of this problem. So there are some similar problems that maybe you solved before, like I solved before. Problems like this, when you have array, yeah, and you need to look at basically you have look at all elements with the same remainder modulo d. So you look at all elements with remainder modulo 0, so it's a block of size b. Yeah. So you look at all elements with step. So you look at all elements with step b. So you look at elements 0, b, 2b, 3b, and so on. Then you look at elements 1, b plus 1, 2b plus 1, and so on. So you look at all elements with remainder equal to 1. So you look at these elements, this element, this element, this element. And you they jump like this. Then you look at this element and jump and so on. Then if you do it like this, then in total you will have linear algorithm. Yeah. So basically you have like b sequences, and the length of each sequence is like n divided by b. Yeah. No, roughly plus minus. Yeah? So you have b sequences, each has size n divided by b. Total time complexity is linear, because it's b multiplied by n divided by b. And what I want to do here, I want to do kind of, I want to do similar thing. So what I want to do, I want to try to calculate some number of these sequences such that total size of this set is linear. Let's do it like this. So let's mark somehow. Let's split somewhere and calculate this sequence. Now, let's look at this smallest segment here. What was this? I have segment one. Let's do next. Let's do another one. So imagine you have a lot of these elements. Many elements. And you split them. So you just break your cycle anywhere, just between first and last element. Just in the beginning. So this element 0, this is n minus 1. Yeah. So just break this cycle here. Doesn't matter where actually. So you can break it here, and just solve the problem when you have this break. So we have 3, I have 5, and another 4, another 3. Then you calculate this thing. Let's find the smallest element, smallest block. This block. Yeah. Now, the optimal solution must break this block somewhere. So, in the optimal solution, there is at least in one of these points, you should have the break between blocks. So, because this solution has maximal possible length, which is not greater than b. Yeah. So, in optimal solution, somewhere here must be the border between two segments. And now, if size of this block is b, then in total I have no more than n divided by b blocks. If I manage to calculate each situation in n divided by b time, then I take b possible starting points. For each starting points, I calculate in n over b. So total time again will be linear. Okay. That's a difficult problem. Okay, I admit this problem was difficult, maybe too difficult for you. Okay. Okay, I'll try to make next contest a little bit easier for you. Okay. And again, how do you calculate this in n divided by b time? You do it by pre-calculating all the jumps. So what I will do, for each position on the cycle, so I have this cycle. For each position in the cycle, I will calculate the jump. So I will calculate, if I'm standing here, how far should I jump? So this sum is not greater than b. So you calculate maximal number of elements you can take from here. So the sum of this element is not greater than b. You can pre-calculate it using two pointers methods. If you're not sure how to use 2 points method, I have a perfect. I will advertise myself. I have the perfect class here. So here I have a perfect lesson about, where is it? 2 pointer. It's actually, I really like this lesson. So if you don't know how to use 2 pointers method, just you just watch these videos. Very nice explanation. I will tell good things about myself always. Okay, so we don't spend time here to play. So again, it's pretty standard thing. So if you don't know how to do it, just learn how to do it. It's not rocket science. Very simple thing. So again, this part is pretty standard, but this part is not very standard. So again, you first calculate these jumps. This is standard part. If you never did it before, just try to do it. It's not that hard. And then this is not trivial part. So you find this smallest part, pick all the points inside this segment, and try to start your doing these jumps from this point. So you pick one of the starting points. Then do these jumps, and calculate how many jumps you make until you make the full circle. And you make no more than n divided by b jumps, because you pick the smallest segment. So you do n over b jumps in each time, and you have b possible starting points. So total time complexity will be linear. Okay, there are other ways to solve this problem actually. So you can look at, okay, after you build these jumps, you can look at the structure of these jumps and just investigate there. So it will have some cycles, basically. You can look at this, and it doesn't matter. So there are other ways to solve this problem also, but I believe this is the easiest one. But yes, this problem was obviously too hard for you. But again, it was too hard for you. It doesn't mean you didn't try to solve it. Try to solve it. Okay? It's not impossible. It's just hard. By solving hard problems, we learn how to solve hard problems. Okay, that's okay. So I think we're done for today. I will post next contest tomorrow morning, probably. Yes. So see you next week.